Hello, good evening, good morning, good afternoon, everybody, wherever it might be. It is my great pleasure to introduce BRAM MESLAND. We met ages ago, first time. I think it was some wonderful conference in Oberwolfa.
Yeah, it's very long ago now.
Very long ago, but it has some embarrassing details, so I will stop speaking about it because it's going live on YouTube. Anyway, we can do it after we stop recording. And now this is something which is particularly exciting for me because it's joining the mainstream non-commutative geometry with the spectral triples with the work of my life, the compact quantum principal bundles. So I'm very happy to have you here, and I'm sure it will be exciting. Now the Zoom is yours, take it away.
Thank you very much for this introduction. Yes, I will talk about some joint work with Branimir Kacic, who's also here. This paper appeared on the archive already 2 years ago and has only recently been published in CMP. And as Piotr said, this will be about non-commutative Riemannian principal bundles. I will start also with a disclaimer that, of course, the most interesting direction here is where you have an actual quantum group acting and so on. But I will fixate in this talk compact Lie group G. So that's in that sense not a completely quantum setting, but first things first. And A will denote a unital G C-star algebra, so a unital C-star algebra on which this compact group acts strongly continuously by star automorphisms. And this, for the setting of this talk, well, this is not yet principal. There has to be another assumption which has been around in the literature, which we will come to soon. But this is the setting, and we will then define a notion of spectral triple, which can be viewed as the notion of a non-commutative Riemannian principal bundle. So in the commutative case, we have a manifold P with a surjection onto another manifold B, and an action of this compact Lie group, a free action of this compact Lie group on this space P, which is nice and smooth and so on, so that B is the quotient by this G action. And then you obtain the C-star algebraic data by simply setting a, well, I'm working in the compact case. So our paper works in greater generality, so with a non-unital C-star algebra, so that we can also cover, for instance, symmetric spaces, so G mod K type principal bundles where G is non-compact and K is a maximal compact subgroup. But as often happens in non-commutative geometry, the non-unital case is substantially more complicated in terms of details, but not in terms of essence. So I will leave out all the approximate units and so on. And so if we set A is equal to the continuous functions on this P, then this is our GC-star algebra. And then the algebra of continuous functions on the base can be identified with the fixed point algebra of this GC-star algebra C of P. So all f's for which alpha G, f is f for all G and G. So the elements that are truly pointwise fixed by this G action. And then this map here we call pi, and pi induces in particular. So pi is a nice Riemannian submersion, meaning that it is a submersion of these manifolds respecting some Riemannian structures, and it induces in particular a wrong-way map from the topological K-theory of P to the topological K-theory of the base. space. So this is not the usual induced map coming from pullback of vector bundles, but it is some other element that we will say a bit more about that goes in the opposite direction. That's why it's called a wrong-way map, and it's denoted by this shriek symbol. And in fact, this pi shriek is induced by what is called the Kasparov product with a specific element in the group. And now I will switch to, well, not 0, it depends on the codimension. In the bivariant group from C of P to C of B. And for my spectral triple approach to this non-commutative principal bundle, this element will be guiding in the sense that not actually the KK element, but some explicit representative for it, which we will view as this analog of this map here in the non-commutative setting. So let's switch pages. So in let me give a definition which is due to Elwood. See where I have it. Yes, so a G-C-star algebra, it's called principal if the map, which I will maybe denote by phi, from just the algebraic tensor product of the algebra A with itself into the continuous functions on the group G with values in A, defined by phi of an elementary tensor, and then I have to make of that a function on G. This will just be alpha G A1 times A2, has dense range.
Yeah, but you are taking an extremely special case of Elwood's definition, right?
It could be that he has a more general definition. I must admit, I might not be familiar enough with that. So, can you cook up the?
Yeah. I mean, so he has full generality. That's why, you know, his name is usually mentioned in this context, because he brought up something non-trivial to the picture, but this non-triviality was because he was really working in the non-unital case. So not only he had quantum groups, not classical groups, so he was using coaction, not this
right.
CGA. But that's a piece of cake. It's just a rewriting of the same thing. But what was really tough, it was really tough to recast Voronovich's density conditions, with which quantum groups are defined, compact quantum groups are defined, in this non-unital setting using multipliers, strong continuity, and stuff like this.
Right, but this, so, and that's actually, so I'm not fully aware of the subtleties, but this means that there would be a non-compact quantum group sitting here.
Yes.
Yeah, okay, I can imagine that is much more complicated. Yes.
Yeah, it's much more complicated, and he had sort of separately the proper action condition and freeness condition, and he managed to do them separately. And this was really nice work, because what people tend to forget, that when you go unital, Elwood's definition is just an almost trivial generalization of Voronovich's definition of a compact quantum group. Because to define a compact quantum group, you have to define what the antipode is, but you cannot just write a map. It doesn't make sense. So a great discovery of Voronovich was that you defined that the compact quantum group is a compact quantum semigroup with free action on itself.
Right.
So the only thing that you have to do in Voronowicz definition is to say that it's not just H tensor H, but it's A tensor A and A tensor H on the other side. But it's the same map, the same story.
Right.
Same density condition.
Yeah. Indeed, this is a very simple case. I fully agree with that, and luckily so, because we're going to be dealing with some other subtleties coming from differential geometry. And in fact, yeah, there are many reasons for us in our work why we actually, well, I wouldn't say had to work with a compact group, but it's really not obvious how to generalize already. Just staying in the group setting to generalize things to a non-compact group. As I said, the subtleties that arise in the non-unital case are really very big. But the non-unitality that I was alluding to was only referring to this algebra here. With that one, we can take non-unital.
Yeah, that's no problem. Yeah. It's usually it's a non-compact fiber which is an issue. You can have non-compact base. That's no problem.
That is much harder. Yes, indeed. So we call this principle, and in fact, it is the case that if I have G acting on some topological space P, then CP is principal if and only if, as Piotr already alluded to, the action of G on P is free. So this G acts freely on P. So here you have your, I would say, well-known notion of a topological principal bundle in a setting where everything is compact. So we want to generalize this to the Riemannian setting, and for that, wait, let me write this down. So, principal G C-star algebras in the above sense can be viewed as non-commutative topological principal bundles. And now we want to go to the setting of non-commutative differential geometry a la Kohn. So via spectral triples. I will give a more detailed definition probably on the next page, but most of you will have seen. So a spectral triple is a datum like this, and sometimes there are more decorations. We'll also sometimes suppress some of the present structures in this talk because it can get very it can get a lot to write, and sometimes you obscure the essence of things, but it's often important to have things like gradings and all that correct, although I will not always be extremely precise about that in this talk. But a spectral triple consists not only of an algebra A, but also of a Hilbert space and an operator. And we have G acting on all of these in a compatible way. And then we need some further axioms to actually be able to speak of a non-commutative Riemannian principal bundle. And I will motivate this by arguing that such an object should have an analog of this submersion pi in the context of unbounded KK theory. So I will also have to give you some definitions regarding that. So for this slide, I would just want to say there are now more objects, so the Hilbert space and the operator, to take into account, and this definition of Elwood of principality is not enough to capture a Riemannian principal bundle. Okay, so let's first give the definition. Well, let me immediately write G spectral triple. And again, I will emphasize G is always compact, so my definition will be a simplification of what you would have to require in the non-compact case.
I want to make a comment about the classical case.
Yes.
This is something that Piotr and I have discussed. If we have a compact Lie group, a compact Hausdorff topological group, and it's acting freely on some compact Hausdorff space, right? So we all know what that means.
Mm-hmm.
That action in the setting that I've set here, compact Hausdorff topological group and a compact Hausdorff topological space, the action is free. That might not be locally trivial, that action.
Mm-hmm.
And classically, when mathematicians talk about a principal bundle, they mean locally trivial.
Right.
Now, for Lie groups, everything is all right. I mean, a Lie group acting by a smooth action on a manifold.
Yeah, certainly. Yes.
Okay. But classically speaking, I mean, when mathematicians, differential geometers, for example, when they talk about a principal bundle, they mean that it is locally, that the action is a locally trivial action.
Certainly.
And
yes, that the bundle has local sections. Yes.
Yeah, but if you go to, there are very simple examples that show that if you talk about compact Hausdorff topological group and compact Hausdorff topological space, a free action in that context, the free action is not necessarily locally trivial.
Right.
Yeah, but even more relevant, if you have a Lie group or even a finite, excuse me, a finite group, if you have a free action in the sense just explained on a unital sister algebra, I think that you can cook up, I'm not sure if Mariusz Tobolski is in the audience because he devoted his PhD thesis to it. No, I don't see him. But we were playing with lots and lots of examples. Now that finally we have a definition of local triviality of compact quantum principal bundles, and we can make sense out of it. It's not automatic that if you have a finite group acting on freely on a unital sister algebra, that it is locally trivial.
Right.
So Paul has a point here. You are taking a Lie group, so you are safe. You are really safe.
I'm taking a Lie group and a nice action on manifolds.
Exactly. That's locally trivial. That's locally trivial. But the moment you replace it with a sister dynamical system, just they have a Lie group is not enough.
Yeah.
You might still have, I don't remember an example, and I'm not even 100% sure that it's true because it's been some time. But I think that we're playing exactly with the cases where you have a finite group acting freely on a unital sister algebra, and either it is locally trivial action or it is not. So that's, even with graph sister algebras, we have some nice examples.
Yeah, it can get, as usual, quite wild when you, when you leave the smooth setting.
Yeah.
Well, so there are these distinctions, classically speaking. However, for Lie groups with a smooth action on a manifold and a Lie group, then everything is on. I mean, then free implies locally trivial. As you say, there will be local sections, and that gives local triviality. Okay.
But only classically, only classically. It's no longer true in the setting he's speaking about.
Okay, all right.
Sure, but
okay. Thank you.
In that setting, that's.
Thank you, Pierre.
All right. Consists of, well, let me actually instantiate this. AHD, and this is again a familiar definition. So this is a Hilbert space H, possibly Z2 graded. As said, this is extremely important, but I will not focus on those details because it obscures things a bit. And then well, let me call it a representation. G into the even unitary group of H. So E just acts by unitaries on H. A is a star algebra. Well, I will actually say a G invariant star subalgebra of B of H. So this means that if I, and I'm not assuming it to be norm closed as usual, but the closure is then a C-star algebra, which I will denote by straight A. And then there is an odd self-adjoint G invariant operator such that the resolvents are actually compact operators, and for all A in this star algebra, dA is bounded. Now, of course, we have to assume that this dense domain of this operator is a nice G-invariant domain, and yeah, you always have to be very precise about such things. You may want that also to consist of C1, that there is a core consisting of C1 vectors for the action. Just in light of the previous comments, I will be dealing with all kinds of niceties there that I may not always emphasize, because the point of our work is to understand the nice case, actually, in terms of these spectral triples.
A spectral triple is a non-commutative manifold. I mean,
yeah, well, in some sense.
Well, what's being axiomatized here is the Dirac operator of the spin or a spin C manifold. This is not a non-commutative topological space. It's much more than that.
It's more than just a topological space, but it's in the way I'm looking at it now, it's slightly less than a manifold. It's somewhere between a metric space and a manifold. Okay. If you want to really recover the manifold, you need to impose much more, as we know.
Yes.
By,
yes.
Some hard work of several people,
yes.
10 to 15 years ago.
Yes.
Okay.
And this is sort of an undecorated spectral triple, which, so such an element in particular, AHD defines a class in Chemology, and in this case in equivariant Chemology, so of the C-star closure, and it's a very refined element. Now, given such HHD, we can take the fixed point algebra and the fixed point Hilbert space and restrict D to it. So write DG, which is also a spectral triple. And as we've given this Elwood's definition of principality, which only pertains to this algebra A, we now want to, well, let me say, inclusion of the fixed points into the algebra A can be viewed as an analog of the surjection from P to B in the commutative case, because that would just correspond to the pullback of this map. But as I said, I want to focus on this wrong way map. And so we wish to describe NC principal bundles as well, Riemannian, as a particular kind of morphism between the spectral triples AHD and HD, HG, BG. But what is such a morphism? Well, that's a notion that has not been completely solidified, but there are different proposals, and I will take the approach by bivariant Kasparov theory and using the explicit cycles in that setting. So we will use a notion of morphism or correspondence motivated by unbounded picture of Kasparov's KK theory. And so KK theory is a bivariant homology theory for C-star algebras. I will assume all my C-star algebras are separable. And associates
to report a gas leak or
to a pair of C-star algebras A, B. Let me say two abelian groups KK0 of AB and KK1 of AB. Such that, well, if I take KK star of C comma B, then what I get is something that's isomorphic to the C-star algebraic K theory B. And if I insert the complex numbers in the second slot, I get the K homology of A. That's basically the definition. And wait, let me write it as follows. The main feature of this theory is the Kasparov product, which is a coupling which allows you to compose elements in these KK groups. And this is associative, and it has all kinds of nice properties. For example, star homomorphisms induce elements in this group. But the general picture, as quite majestically pioneered by Kasparov, uses Fredholm operators and so C-star algebra and some extra data. Before giving, so KK theory is sort of notorious. It can be, or it's yeah, there are many subtleties and details, but before giving some more abstract definitions, let's give a description.
I have a question, quite general. Suppose that your C-star algebras A and B are commutative, unital. Okay, so they correspond to compact spaces. And now you can just consider a plain continuous map between these compact spaces. This gives you, via pullback, morphism between C-star algebras, and each morphism between C-star algebras produces an element in KK, yes? But there are a lot of equivalent elements in KK. There are equivalence relations. So how strong is this notion of being equivalent in KK in the commutative setting? This is somehow stronger than homotopy equivalence?
Well, it is basically homotopy equivalence. If you
No. It's much weaker than that.
Yeah.
No, it is not basically homotopy, not at all.
How do you view this, Paul?
I think if you have two compact Hausdorff spaces whose K theory is isomorphic, whose K theory, just as the abelian groups, is isomorphic, then they will be KK equivalent. Certainly. It's much weaker. It's far weaker than homotopy.
No, it's weaker than homotopy equivalence of the spaces. But if we have two maps between spaces, okay, homotopy equivalence is the relation you impose, but so homotopy equivalent maps induce the same map or the same element in KK theory.
Well, yes, that's right.
Yes, but it's the actual equivalence relation is coarser. Certainly.
Wait, I want to have a question in the direction you are going. Let's say, classically speaking, we have a good situation. We have a principal G bundle. Just in the classical case. This is more or less characterized. I think it's essentially equivalent that in a straightforward way, it's straightforward, I believe, you get a Morita equivalence, which is a KK element, right? I mean, KK can be thought of as a huge generalization of Morita equivalence. I mean, that's one view on KK. All right. So we have, classically speaking, a principal bundle. Let's say it's locally trivial. We all agree what that is. And in a rather straightforward way, you get a Morita equivalence between the functions on the quotient space and the cross product.
Yeah.
And it seems to me you are moving in this direction.
I'm not sure. Maybe you can comment on it later if your suspicions are confirmed.
Because I think that's an interesting point of view, that the essential point here is the Morita, a straightforward Morita equivalence between the functions on the quotient. So this would be the invariant functions, right? The A upper G, and the cross product C star algebra.
Yeah, so you're talking about this one.
This pretty much characterizes principal bundles.
Yep.
Yeah.
And I think you are bringing in spectral triples, which seems to me to be a very good idea. But somehow I think that you are moving in this direction here.
Well, let's see if that is so, because I cannot at the moment see what you have in mind, but let's see. I was going to sketch how to think about KK theory in the manifold setting.
Okay.
And this is also
Well,
old work by Cons Scandalis and later
right.
geometric models for chemology have been studied. Well, Paul Baum is certainly a name there. First,
if you take what I did a long time ago, when I was young, I used to say to Alain Kahn, well, we did these things when we were young and foolish. And Alain would say, no, Paul, you have it all wrong. We did these things when we were young and beautiful.
And
so anyway, if you take what I did, the geometric model for chemology, this goes over very nicely, very easily to KK, to KK theory. But we can discuss this later. Okay, please.
Yeah. So elements of the group KK. So now M and N here are two manifolds, maybe nice Riemannian manifolds. Again, I want to only focus on very nice settings to get the conceptual points across. And these are given by what Cons Scandalis called correspondences. And a correspondence is a diagram of this form where Z is a manifold and E is some vector bundle, finite dimensional, locally trivial vector bundle over Z. And then there are two maps, and F from Z to M is a proper map, and certainly continuous, of course, maybe even smooth. And G from Z to N is what is called K-oriented. And this means that the existence of a certain spin C structure on a certain vector bundle in the setting is required. That's the key axiom here. And in our case, we have a very simple such correspondence in the commutative case of a principal bundle over some base. The correspondence you're looking at is this one. And here we just have the identity map. And that satisfies all the axioms. And you can describe KK theory entirely in terms of such diagrams where the theorem of Kohn and Scandalis was indeed that so the group KK C0 of M C0 of N is exhausted by such correspondences, and the Kasparov product so if I have three manifolds then the Kasparov product of two such correspondences is given by a quite simple fiber product type construction. No L. so we have the fiber product of the manifold Z and some type of tensor product of the two bundles, and that gives us, provided the correspondences are transverse, this gives us again a correspondence, and this result stands in stark contrast with the original construction of Kasparov of this product, which is very intricate. And here you see that this, at least on a topological level, this can be understood in some much more intuitive manner. So in this context, you would say, okay, morphisms of manifolds are not just maps. Maps are also fine. They are particular cases of such diagrams, but we add some more. And because what's important here is that, again, modulo some conditions, you can actually write this composition on the level of the cycles, like before taking the equivalence class.
Well, you might have to wiggle a little
Yeah,
bit.
you might have to fiddle because you need them to be transverse.
Yes,
Certainly.
right. But that's all right. That's okay.
So you have to find a nice representative, and then you can do it.
Good. Okay, good.
Certainly so. And this leads me to the unbounded picture of KK theory. Actually, now that we're here, there's some kind of Condrendu note, I think, on this bivariant picture, apart from Conan-Scandalis' paper, but it's very hard to find. So the full bivariant group thing, there's no nice expository article about this.
I think that there might be a Condrendu note by Jonathan Block and me, I think.
Okay.
Is that what you are referring to?
No, I once saw some Condrendu note by Conan-Scandalis from the same time, but it's very hard to find. So there is, of course, the paper where most of this is done in section 2, and then there is an appendix where they characterize the Kasparov product in the operatorial setting. But there is also, I think, some note which exposes this theory purely in the commutative case, in the full bivariant setting, and so on. But I don't know if I remember this correctly, but I thought, Paul, you would be the person maybe to know this.
I mean, basically, you take.
Here's a suggestion about Rosenberg-Szabo. In the chat.
This one I'm also aware of. That's much more recent. Yeah.
I mean, basically, you take the geometric definition of Chemology and you generalize it. But we can discuss this. Okay. All right.
Yeah, let me just continue to get where we want to get. Yes.
Okay, good. Yeah, right. Please continue. Yes.
But Bram, sorry, just before you continue, let me ask you a stupid question. Is it really necessary here at this point to take the same M as you take here, or can it be M and N?
Well, these are M and N, or they're yeah.
Okay.
Maybe that,
okay.
That's a problem of handwriting. So
okay, good.
That's certainly M, and that other one is an N.
Okay, oof, that's a relief.
yeah. Okay, so if we have a pair C-star algebras, then an unbounded KK cycle for AB is a pair XS where X is a right Hilbert C-star module over B. So this means that X is a right B module that carries also a B valued inner product. I will not go through these definitions because I hope most of you will have seen that. And there is some positivity and a nice norm associated to the inner product. And this thing is the Banach space. And A acts on this module acts by what are called adjointable operators, which I often denote by n star to emphasize that they have to have an adjoint. So these are linear operators, bilinear operators that also have an adjoint with respect to the inner product. That's a non-trivial condition. And then this S is some densely defined operator on some densely defined submodule into X, such that, and so the definition looks eerily similar, such that the operators S plus minus I inverse are actually well defined and adjointable. This is a non-trivial condition referred to as regularity in the literature, and these should be compact endomorphisms in the sense of Hilbert modules, and the commutators of S with A are bounded for all. Well, maybe I should have actually instantiated this as I did with the spectral triple. So the curly A is a dense subalgebra of A. So this is the same definition as the spectral triple, but now we've replaced the Hilbert space by a Hilbert C-star module. And these elements define every element in a KK group, and therefore they could already be viewed as an approximation of what maybe should be a non-commutative morphism. But as we saw in this theorem that's still on this page by Cons Condalis, and which I wiped under the rug, is that this composition of the fiber product, it involves the correspondences being transverse. And it's an extra condition that is relative in the sense that if you have one correspondence, then you cannot, or then the transversality is defined in terms of the other one before you can compose them. And that's, as Paul mentioned, why you have to wiggle them. And to define the Kasparov product of such unbounded cycles, there is simply not enough information in them to do this on the nose as such. So we need to look at more refined version of these cycles to get the right notion of morphism. I should really speed up a little bit. So now I defined what a KK cycle is for two C-star algebras, but as with the commutative correspondences, things become a bit better when you fix spectral triples. No, I want a 0 here and a 1 here. Yeah, all right, this is T. So I'm fixing two spectral triples now, not just C-star algebras, but really two spectral triples, and this means I also have designated dense subalgebras.
Sorry, Bram, did you write it in French? Les spectral triple here?
No, let AHD and let AHD and BHT be spectral triples.
Okay, B, okay.
Then a correspondence between AHD and EH T is given by well, I'm writing it as a triple now. So I have a curly X that's supposed to be, I have an S, and I have a new object nabla. I will explain what it is in a minute. Which consists of I will say a pre-C star A B bimodule curly X. So I'm not assuming this to be complete. I have these two dense subalgebras and I have some bimodule between them. You should think of compactly supported smooth sections of some bundle here. And then an essentially self-adjoint regular operator S defined initially on this X. So this X, curly X, is in the domain and it goes into the C star completion. So the straight X is the C star completion of this curly X such that a curly XS is a KK cycle in the sense of the previous definition, which means that, okay, this S has compact resolvent. I should make this X straight now.
And what do you mean by regular operator, if I might ask?
Regular means that that means that these operators are well defined. So another way, there are many characterizations of this. This should be surjective. This is one of these conditions that in the Hilbert space case is automatic, but in Hilbert C star modules can fail. It's a technical axiom.
Okay. Okay.
Which ensures that your resolvents exist.
Okay. Fair enough.
And now we have this third object, nabla, which is a connection. And here you see, so you see that I've been using more than having just two C star algebras already, because I was speaking of a bimodule between the dense subalgebras, and that bimodule should be the initial domain of this operator S. But now I also want to introduce this notion of connection, and for this I am introducing the space of one forms associated to the base spectral triple. So you form linear combinations
But is your right-hand side here curly X or just X?
No, it's curly X, yeah. Curly. Very curly X. No, so the curly X features as the common domain for everything.
Mm-hmm. Okay, but I meant the right-hand side. It goes into...
No. The right-hand side is the straight X,
straight
and this
X, okay.
is also a completed part, which I will say something about.
Aha, so this is non-algebraic, okay.
Yeah. This is very important. Okay. So this omega 1 of T is a subspace of B of H1, as you can see, because it uses both representation of B and the operator T, and this is the analog of the differential one forms on a manifold, because if you have a Dirac or a Hodge-de-Raam spectral triple, then this space is exactly the differential one forms on the manifold. And here we have, so a spectral triple gives you an analog of that. automatically. I'm first taking algebraic combinations and then take a closure. And that's what is called an operator space. I will not say a lot about this, but this is an operator space. It's not an algebra, but it's a closed linear subspace of this B of H1. And it also has a bimodule structure for B. And there is a derivation delta T from B into this omega 1. Just by taking these commutators, and then the completed tensor product here is the so-called Hogger tensor product, which is maybe not as well known, but it is actually the tensor product that's compatible with the Hilbert C-star module tensor product, in the sense that the tensor product of two Hilbert C-star modules is isometrically isomorphic to the Hogger tensor product of these two modules. That's a result due to David Blecher.
Wait, could you state that again, please?
Let me write a bit when I say that. So if I have two Hilbert C-star modules and I take the Hilbert C-star module tensor product,
yes,
that's isometrically isomorphic to the Hogger tensor product of the same objects, where you have to view them as operator spaces, and this you do by embedding them in the linking algebra.
Okay, thank you.
But since my module of one forms is not a C-star module, I cannot speak of the C-star module tensor product, but I can still speak of this Hogger tensor product. So that's why it comes in. And I need a completion that's compatible with the Hilbert C-star module completion. So this is, there are a lot of subtleties and details here, but this is somehow forced upon you when you work in this context. Also, the Hogger tensor product is very nicely compatible with operator multiplication. So the multiplication map from a C-star algebra tensored with itself is continuous for the Hogger norm. It's not continuous for the usual C-star algebra completions of the tensor product. So for algebraic purposes, this is a very nice thing. And this connection is a linear map satisfying the following identity. Which is the usual Leibniz rule for connections, but now relative to this second spectral triple. And this is the data, and now it will not fit on my page to write the further requirements. But if I have this data, then I further require that AHD is isomorphic to, and I will tell you what I mean by this notation, X as nabla tensored with BHT, where this last thing is defined to be the following object. And the isomorphism sign is, so there's again more stuff to explain. So the operator one tensor nabla T is initially defined on the algebraic tensor product of the curly X module, and it goes into the completed tensor product of X with H1, and it's defined as follows: X tensor TH plus nabla x acting on H. And the reason for this definition appearing is that if I would just take this part, the 1 tensor T part will not be well defined because the operator T doesn't commute with B, so it's not defined on the balanced tensor product. And it turns out that the correction term to make this well defined is exactly given by the term coming from this connection. So then I can define this product operator, and this symbol here means that I want the difference of my operator D in my spectral triple minus this sum. And for our purposes, let's assume we're in the unital setting. It's bounded and commutes with A. So what I'm saying is my correspondence, my access nabla, is giving a factorization between my two given spectral triples in an explicit way. And we have the operator D consists now of a vertical part, of a horizontal part, and an error term here. But that error term is somehow inconsequential because it's, well, in the unital setting it's bounded. In a non-unital setting you need to require some more subtle things. And it commutes with the algebra, so it doesn't see.
So that's what you called a remainder in your abstract.
Yeah, I will get to that. Yes, it takes a long time to set up this picture, but this is the remainder. Yes, indeed, and that's because when you well, let me first state the result. If, of course, this X as nabla is a correspondence for AHD and so this is 0 again, AH1T, then it actually turns out that the classes will, so recall that the correspondence, I'm suppressing the connection now because the connection doesn't contribute to the class. But if I have such a correspondence, I in particular have a factorization as a Kasparov product in KKAB. And but I have now a much more refined version of that, because having just a factorization in KK, you could do that in many ways because there is this coarse equivalence relation floating around. And what we're saying is that such a correspondence should be really the analog of the nice, smooth Riemannian submersion that you have between a principal bundle and its base, in the case we're about to get to now. And moreover, up to equivalence, every Kasparov product can be realized in this way. This is a result due to Adam Rennie and myself some years ago. And that's the analog of what happens in the Constandalis picture, where you have to wiggle a bit to make the correspondences composable. In the unbounded picture, you can do the same. You have two unbounded cycles. You can always find a connection, and maybe you have to change the operators, but then once they're well aligned, you can form the Kasparov product in this way.
Wait a second, Bram. There is a comment in the chat. It seems to be a typo. The element lies in KKAC, and the correspondence is XS nabla.
That's right. Well, I will say that's correct. I was writing not x as nabla here because to get the kk element, we can forget about the nabla. So recall that one of the axioms in the correspondence was that AXS is a kk cycle. So that's why having a factorization just in kk theory is much coarser than having this whole setup. So I'm forgetting the connection. I'm also forgetting the dense submodule. I'm just taking the kk class associated to all this data. But yeah, initially there was this connection. What this also says is that if I choose another connection, or then I get maybe another perturbation, another remainder, and so on. This is all for the homotopy level, it's inconsequential, but for the geometric level, it's of course very important. But,
and here, what do you mean by C? Just complex numbers? Or?
No, C can be any. Well, I was writing it for spectral triples, of course, so maybe I should write C. Yes. Let's do that. But you could replace the second element by another kk cycle and everything would still work. Mm-hmm. Okay, so this took me a while, but this is the kind of morphism we are going for. So now let's see how we can get this data in the context of principal GC-star algebras. So now let AHD be a G spectral triple with a principal GC-star algebra. Let me see. In the interest of time. Now consider the conditional expectation from A to the fixed point algebra, which just comes from sending A to the integral over G. So you project on to the invariant subalgebra. This gives us a C-star module completion.
So BRAM, so here you would have problems if G were non-compact.
Exactly. Yeah. This is clearly doesn't exist in the general case.
But you wouldn't have any problem if G were compact. If G were in quantum.
For compact quantum group, this can be done. Yes.
Exactly.
Yes. So this gives us a C-star module, which I will denote by L2V of A, and this is an A, comma AG bimodule. Now I'm being somewhat imprecise, but using some Clifford algebra yoga, we can consider the operator right, dg rho and this is some funny explicit formula, but this is Constant's cubic Dirac element in a version of the Weil algebra that's present here. So I'm using, let me explain to you what this formula means. There is some Einstein summation used, so I'm summing over all the indices that occur up and down. And here, this inner product is a fixed at G invariant inner product on the Lie algebra. And the epsilon I, epsilon upper I, epsilon lower I is a dual pair of bases for G and G star. And rho could be ignored, actually, is what's called a vertical Riemannian metric. And this rho is there, so it comes into all your Clifford representations. This rho is there to encode the fact that already in the classical case, you know that the volume of your G orbits may vary over your manifold. And so you could take rho equal to 1, and up to homotopy, this will usually work, but this would not be the geometrically natural choice. So if you take the Hopf vibration of S3 over S2, then this rho will actually be a non-trivial function, because the S1 orbits vary in volume. But the point here is that this is a natural Dirac operator that is defined using representation theory, and this dg rho the operator dg rho is self-adjoint and regular in the module that you get from this conditional expectation. And I will say again, I am wiping some Clifford analysis under the rug here. And so this is a natural operator that always works.
BRAM.
Yes.
Ludwig, hi.
Hi.
What is L2V under it?
Yeah, so that's the vertical. So I said there is this conditional expectation coming. Wait, let me go back to this page. So I have this expectation here. which is a map from A to AG. This gives me an AG valued inner product on A, and this denotes the completion that I get from that. So this is some completion of A in a different norm than the C star norm, and it should be thought of as a it's completed. It's L2 in the vertical direction somehow, and it's continuous in the horizontal direction. So that's why I call it L2V.
Okay.
And on this module, there is this natural or this representation theoretic Dirac type operator acting.
Okay.
So this will appear in the factorization. And
You probably want to say L2 of A and not of AG.
That is very true. Thank you.
Right? That's all. I think that's it.
Okay. That was the, okay. Sorry, that was the confusion. So now the proposition is that if A is a principal GC star algebra in the sense of Elwood, as we saw in the beginning, then A L2V of A over this AG with this DG row is an unbounded KK cycle. So this object I always have. Once I have a principal GC star algebra, then there is a very natural KKG cycle that is just always there.
And can you tell me one more time where do you use principality, the freeness assumption, to have it as a KK cycle? What would go wrong if your GC star algebra wouldn't be principal?
I think it's the compact resolvent.
Okay.
That's where you need to work. So this is where we use a result of Kenny de Kommer and Makoto Yamashita, which you have to prove something about the isotypical subspaces and the way this operator behaves there.
And which paper is it?
Of the Kommer and Yamashita?
Yeah, I have here from Branimir, quantum associated vector bundles. Yes, yeah. I know there is a crucial lemma. We used it with Paul. Paper that the associated quantum vector bundles are finitely generated projective modules. This finite generating projective is very tough thing to prove.
Yes.
From the Elwood condition.
We had to use a non-unital, or the version for non-unital A for that, and we actually, this was curious because we couldn't find this kind of statement in the case of just a classical group as we were looking at. We had to use their quantum group version of things.
Yeah. Because here things get complicated when you go quantum. That's true.
Yeah. All right. So now we come to the remainders. Oh, right here. So let me just say, let AHD be a G spectral triple. And again, I'm assuming that A is unital. The remainder is an odd G invariant bounded operator Z in B of H. So that's just a very general definition that doesn't tell you very much. But we can use this remainder to say what we mean by a principal spectral triple. And again, I'm not very organized with my notes. So the remainder is strong if, when I take d minus dv minus z, and I take my commutators with a, then I land so I call the remainder strong if the commutators with a actually land in the closure of a times times the commutators with just the base. So this is what is in the more algebraic literature called a strong connection.
I wonder if Piotr recognizes his definition.
Yeah, I'm also wondering about that.
Well, so am I.
Hmm?
So I'm also wondering, yes.
Sorry, Bram, but you might want to explain what the vertical Dirac is.
Yeah, I wanted to ask this question. Thank you, Riemannian.
Oh, wait, sorry. Yeah, but that was what I called this DG row upstairs. So that was the operator that acts in the module, which can be well, maybe I should actually do it like this. So dv would be GG row tensor 1, where we have this module L2A with coefficients in AG, and if we tensor that with the fixed Hilbert space, we get back our big Hilbert space. And so dv is the representation of the DG row on H. And so we subtract that from the full D, but we also subtract this remainder. And it turns out that in examples, you really need this remainder to achieve this. And then some magic happens, because once you have this condition, you can actually use this commutation to construct one of these module connections that I talked about before in a canonical way. And here you have to do some analysis. But once you have this, you can do that. So that's another proposition.
Let me just quickly comment. I mean, the way in which I recognize a strong connection condition is that the reason I came up with it ages ago was because I wanted to make sure that a principal connection on a quantum principal bundle induces a module connection, and this is when I needed this condition.
Yes, yeah. So that's also why we wanted it, of course, because that's what the KK's factorization should encode. It should encode the splitting of a principal induced by a principal connection, where you split the vector fields into horizontal and vertical ones.
And only later on it turned out that this is perfectly in line with purely algebraic Hopf-Galois theory, that is actually existence of a strong connection is tantamount to faithful flatness.
Yeah. So given a strong remainder Z, there is a natural module connection, nabla Z, defined on the dense subspace of this vertical module, given by just A, because the vertical module is a completion of A, modulo Clifford relations, into the vertical module tensored over AG with the one forms associated to the invariant operator, DG. So DG comes from AG, HG, DG, the invariant spectral triple corresponding to the base. So we take the forms with that. And there is the Hager completion here that was so important. So this is a non-trivial statement that from this more or less algebraic commutation relation, where you take commutators with A and you lend into A times commutators with AG, you can actually canonically induce such an operator. And for this, you need to use some tricks. You need to use a nice frame for the module and then show that certain series converge. So there are some estimates to be done here that are quite non-trivial. But I think it's very nice that this algebraic notion of strong connection is really compatible with this module connection that uses the Hager tensor product. So, and then
it's compatible with many things.
Yeah,
is also compatible with things in category theory, because another way to formulate principality condition, as is in our paper with Paul Baum and Kenny de Kommer, is that the functor of associating projective modules to representations, that this is strongly monoidal. That's equivalent again to existing of a strong connection. So category theory, algebra, algebraic geometry, function analysis, spectral triples, it seems to be compatible with all of it.
Yeah, no, and so let me take it. Well, I've already done it, but this Hager tensor product, for the same reason, I like it very much, because it's compatible with many algebraic constructions.
Exactly, yeah.
Which is why, yeah, it really helps in unifying the algebraic framework with the operator algebraic context. So then our result then says that let AHD be a G spectral triple with a principal G-C-star algebra and Z a strong remainder, then there is a correspondence
Bram, I don't mean to rush you, but you have by now -1 minute left.
Yeah, but this is the last thing I'm saying. Between the spectral triples AHD and AGHD GG, where I will again emphasize that the remainder is very important to get the connection. You cannot just work with D minus dV. You have to correct it. And in geometric settings, there are natural choices for this remainder. And it usually corresponds to some curvature information underlying the bundle. But you really see that this notion of principal G spectral triple, it unified the algebraic approach with the KK approach. And yeah, it's also one last thing is that this whole setup is compatible with theta deformation. So if you have it for some algebra that carries an extra Zn action or a circle action that you can theta deform along, then this factorization remains stable. Of course, as I said in the beginning already, the Q deformations is a whole different story. These are much more complicated, but this was an important first step, I believe,
I agree,
in connecting the two approaches. All right, thank you very much.
Okay, thank you very much, Bram. This was a very exciting talk. And now we can go into questions. I would start from Branimir. Branimir, you had some comments at the very beginning in chat, so maybe now we can speak freely and say them aloud.
There's nothing terribly consequential. It's just an observation that it's a classical result of Gleason that that for a compact connected Lie group acting on a locally compact Hausdorff space, free is the same thing as principal. And the other thing I wanted to maybe mention
that is not true. We've already discussed this, and that is not a correct statement that you just made.
There's a kind of topological slice lemma that Gleason proves.
Yeah, but I'll give you a very simple example. Let your group G be S1, right? It's a compact group.
And the Lie group?
Oh, he wants completely regular. Sorry. He wants completely regular. Sorry, please continue.
I mean, we have already discussed this, but...
yeah, so there is an extra condition in Gleason's theorem, you're saying, Branimir?
Yes.
In the context of Lie groups and smooth actions of Lie groups on manifolds, there is no distinction between free and locally trivial, and this is a principal action. But if you enlarge the context, if you go to compact Hausdorff topological groups, acting by a free action on a compact Hausdorff topological space, that action is not necessarily locally trivial. So it's not what mathematicians call a principal action.
Yeah.
But for Lie groups acting on a manifold, fine. This particular technical difficulty does not exist in the smooth, the C infinity context.
Okay, yeah, let's go on.
I'm not. Sorry, I'm not particularly functional today. I'll take the correction that Gleason's theorem proves the appropriate slice lemma in the case of a compact Lie group acting on a completely regular space.
Yes.
So that there is a something to be said there. I guess
I think you are quite right. In fact, I think the appropriate hypothesis is that the compact group should be finite dimensional. And
yeah.
So this was all worked out several decades ago. Yeah, okay. As long as the compact group is finite dimensional, yeah, then I think this distinction between free and locally trivial, there is no distinction. Look, here's the basic example. Take S1 operating on S3 by the Hopf action, right? This is it's smooth, everything is smooth and so on. This is locally trivial. Of course, it's not trivial. I mean, this is not globally trivial, but it is locally trivial, all right? Now I would like you to take S1 and just cross it with itself countably many times. S1 cross S1 cross S1 countably many times, okay? You give it the usual product topology. This is a compact Hausdorff topological group, no doubt about that. It's not finite dimensional, but it's certainly a compact Hausdorff topological group. Now take the three sphere and cross it with itself countably many times. So we have S3 cross S3 cross S3, right? And then we have the evident action of this compact group on this compact space, right? But this action is certainly free, no doubt about that.
Mm-hmm.
But this action is not locally trivial. This is not a locally trivial.
Yeah.
So is this infinite product of S1s a
Paul,
Lie group?
what
group?
does it mean locally trivial in this case?
Well,
Your base space is not finite dimensional, so locally trivial doesn't make much sense.
Yeah,
well, locally trivial means that given any point in the quotient space, right, you can find an open neighborhood of that point such that when you look at the pre-image of this open neighborhood in the total space, the action as an action is isomorphic to a trivial action. I mean, to a locally, the action is isomorphic to a trivial action, to a globally trivial action. And this cannot be done in this case.
Or to put it simply, that meets a local section over this open neighborhood.
Well, the problem here is that the open neighborhoods we are using the usual product topology. The open neighborhoods are too big. And that's I mean, if we work in a C infinity context with Lie groups, then this particular point goes away. But if you want to talk about something that's very topological and so on, then you have to take into account this point.
But Paul, BRAM has Lie group as a structure.
Yeah. We already determined.
So this is a very important point. We are really here strictly dealing with compact connected Lie groups with the de Rham bivariant calculus. Already, we sort of posed the open question at the end of the paper, but I'm now firmly convinced that the Q deformed complex half vibration with the Q monopole cannot be correctly accommodated in the setting of ordinary spectral triples. There's a sort of mismatch in like you have basically have Q squared in the vertical direction, Q in the horizontal direction. Like everything just goes haywire in these sort of two complementary directions. So that's maybe something important to bear in mind. Like we're really using compactness. We're really using the fact that it is the de Rham calculus all the time. The sort of this quantum. I always forget if it's Weiler-Weil algebra. Alexei van Meinring keeps on appearing again and again. You always have this sort of vertical Clifford action that lets you have this vertical Dirac sort of modeled in Costin's cubic Dirac, and this choice of Costin's cubic Dirac is actually all important in making things work on the nose. So in terms of the overall philosophy, I guess maybe one last observation I want to make is the game we're playing is we're starting with some notion of principal G spectral triple with these various decorations of vertical action, a particular choice of a remainder, for which is a canonical candidate that actually works on the nose in most examples you can dredge up. In particular, it recovers the sort of vertical and horizontal operators that in the paper of Dobrowski and Zitaj on circle sort of spectral triples. And then without any reference to unbounded K theory, you can write those as definition, see if examples work, and then you can just sort of everything just unfolds. You can extract this basic piece, which in the absence of a vertical spin C condition is going to be something akin to an almost commutative spectral triple over the true naked base. And you have this sort of longitudinal geometry and index theory encoded by this correspondence. And the horizontal Dirac, this D minus vertical Dirac minus remainder, if you like, there's a sort of underlying strong connection that's spatially implemented by the horizontal Dirac. And this also has another implication that if you're starting from a spectral triple, all the connections you deal with are not only strong, but they're bimodule connections. And maybe one other thing, and then I'll really shut up for good. You can then basically think of variation of the horizontal part as variation of the horizontal covariant derivative. And dealing with this becomes quite non-trivial because in general, the difference between possible horizontal Diracs is going to be something vertical, like a first order non-commutative vertical differential operator, crudely speaking, or pseudo-differential. And what's happening is that you fix the vertical geometry, you fix the basic geometry, you're gluing them together via to form a total geometry, but different choices of horizontal covariant derivatives are not going to give you isomorphic total calculi. But that's a topic for another story.
Okay, thank you so much, Bram. Vladimir, sorry. You guys have the first three letters of your names the same, so it's confusing. Okay, Tomek, go ahead.
Okay, so my question is about the last theorem. You obtain a correspondence. Does this correspondence defines pi lower Schrick?
Yes, in the classical case, it represents that class. Yes.
Okay.
That's sort of the, but actually, yeah. So that's a much coarser statement. So already this module with this vertical operator gives you that class basically. It's so what we've added there. The connection coming from this principal condition gives you really this factorization on the level of unbounded operators. And that, that then implies, using that general theorem that I showed before, that such a decomposition always represents the Kasparov product. That implies that you have pi Schrick here.
So Bram, does it depend on Z?
No. So Z is inconsequential at the homotopy level. But you need to put it in to make this this factorization on the operator level work. But if you could have different choices of Z that are both principal, and then you get different factorizations. But
You do get different maps, or
no,
so
you
by
get
Pythagoras string is the same, right?
Yes. So the
On
Z
KK level, yeah. Okay.
that is an invisible in
Yeah.
KK theory.
Okay.
So you can axiomatize this further and describe a whole class of even unbounded perturbations that don't change the class of your cycles.
Okay.
Nikolai, go ahead.
I'd like to ask whether this choice of Z actually somehow change the, I mean, what is there the connection between the dimension of the original spectral triple, the dimension of this stabilized spectral triple, and the choice of this operator Z?
Well, but the co-dimension is fixed, right? So I didn't pay too much attention to that, but there is, yeah, you need to pay careful attention to the Clifford algebra yoga here, and then you have a co-dimension of this cycle. But the Z doesn't change that because it's G invariant and it's odd. It's just a perturbation of the full setup.
Okay, thanks.
All right, anybody else?
Yeah, but perhaps I could also ask.
Go ahead.
It's Jens.
Hey.
I was wondering. So I mean, Walter and we spent quite a long time thinking about the non-free case.
Mm-hmm.
So is this just too wild to do anything in this generality, or did you think?
Yeah, well, so as I said several times, this is really the very nice case in which we were going for a very nice result. The non-free case, I must say, I have no real idea about there.
Okay.
I don't know if Branimir can comment on this. I have the impression that the vertical operator is already problematic.
I'm not so sure. I definitely the spectral triple on the base is going to be problematic, perhaps.
Oh,
but
yes, yeah.
Both of them. Yeah.
May I comment? Actually, this is Paul's comment. It's really a question of relation between AG and A cross G, right? So you should think of it, if you think about cross product.
Mm-hmm.
So you get splitting in some kind of, I don't know, filtration or something like this. And all the pieces will behave nicely with respect to your construction. So you can use what you did, but point is that the algebras get multiplied by some sister algebras of of stabilizer algebras, right? So problem is you have different in the free case you have no stabilizers.
Yes.
When you have non-free case, you have stabilizers, and different stabilizers will correspond to different quotients of a base, right?
Right. So
and that's what will show up.
Yeah, I guess.
But otherwise, the same construction should work.
Yeah. So you need to enlarge the base setting.
Yeah.
And then
what is it Paul calls this hat classifying space or something? G classifying space? I don't remember.
Oh,
yeah.
Well, the hat space.
Yeah.
That was used to get a good version of equivariant Chern character.
Yeah, but it's a good version of quotient, right?
You could
basically
view it that way. Sure, you could look at it that way.
Yeah, that's what you need here, right?
Well, I think what Richard is saying, correct me if I'm wrong, Richard, that that somehow in some way into what you are doing here, somehow should enter the idea, I believe that that the cross product C-star algebra and the functions on the quotient space, that these two are Morita equivalent in a direct way, in a very evident and direct way, if the action is principal. Is this what you are saying, Roshan?
Yeah, sure. Yeah. If it's not, you have to correct.
Yeah, so
there's an obvious kind of correction.
In a non-free case, you may want to work with a cross product. This is what you're saying.
Yeah, I'm saying the cross product will tell
you have to go through some further.
Yeah, it tells you what you're supposed to write.
Yeah.
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 So let me just say that there is not too many spectral triples on cross products. Just by the way, there are a few papers, but not too many.
Well, in general, of course, there is this whole issue of what you mean by exactly what you mean by the C-star algebra cross product. I mean, you're absolutely right. That in general is an issue. But in the case of a principal action, I think that all the possible C-star algebra cross products are the same. So I mean, that's part of the picture. That particular fact, I think, is part of the picture.
Okay. Branimir?
I might interject on that point. I mean, one thing that is kind of cute is that, so there are spectral triples for Z and sort of metrically continuous Z and Zn actions due to Risad Marcoli, Rehani and Hawkins, Skolsky, Zacharias, White, good lord, White Zacharias. And those fit in quite nicely. They, you know, by the appropriate duality, you can think of them as principal torus bundles. Everything works out quite nice. I mean, these are pretty simple sort of situations, but one thing that is kind of cute is that if you now do sort of this variation of the principal connection, look at gauge transformations, group cohomology just falls out into your lap. So that's one comment to make. And the base is really going to be the original spectral triple you started with. So there's a kind of toy test case for this where you're taking a cross product by Z to the end and asking, okay, by this sort of Morita equivalent situation, I should get a principal torus bundle over the original thing, and that all works out nicely.
Well, certainly, what we have here is certainly part of the picture. Great. I mean, this is part of the picture, and well, this should, of course, onward and upward, but surely what we have here from the point of view of spectral triples, I mean, this has to be part of what's happening here. I think it's kind of interesting. You have these two spectral triples, and then you have the correspondence. Yeah, okay, great, wonderful. Good.
Vladimir, go ahead.
So maybe one last bit of advertising. We can also do orbit-wise extrinsic Riemannian geometry in this setup. We can tell you what the orbit-wise shape operator is, what the orbit-wise mean curvature one form is when you're totally umbilic, when you're totally geodesic. We can do all these things in the setting. And that bit doesn't actually require principality. You just need to have this nice vertical Clifford action. So it's a kind of locally free sort of situation. So
what would be your locally free definition in this context?
Basically, the existence of this nice, the existence of a nice vertical, the existence of a vertical Clifford action, basically such that the resulting vertical differential, vertical exterior derivative gives you a first order differential calculus. So that dual of Lie algebra tensored A really is given to you by, it really is generated over A by vertical derivatives of elements of A. So that's a kind of sort of local.
Okay, so kind of the representation of Lie algebra.
Yeah.
Okay.
Yeah, and so there's a vertical Riemannian metric and a vertical Clifford action with respect to that vertical Riemannian metric, which could have central but non-trivial sort of transverse sort of dependence. And you need something, and there's a way of quantifying the fact that basically the Clifford connection underpinning your D has bounded or locally bounded momenta with respect to your infinitesimal Lie action.
Okay.
Jane?
Hello, hi, Bram.
Hi.
I think I'm on. Okay, very good. So just a very simple question. I mean, classically, when you start with a Dirac operator on a base space, so you have a principal bundle. When you start with a Dirac operator on a base space, and you start with a connection, basically it can define you the Dirac operator on the total space. So you can go between the Dirac operator and the total space. In the U1 case, this is classically done by Amann and Baer.
Mm-hmm.
And this remainder and then this fixing this Dirac, this is strict. So there's one-to-one correspondence between the possible connections. I mean, in the U1 case, U1 connections and the family of Dirac operators that you get from the Dirac operator on the base space.
Mm-hmm.
Now, getting to the non-commutative U1 case, what we needed to have this sort of one-to-one correspondence was the existence of the real structure. I mean, do you need some extra decorations like the real structure, like something like that, to have this? Or does it work only for some connections? Or do you have something like, once you have the connection, where assuming the strong connection or strongness condition for this principal bundle,
Mm-hmm.
do you have for each such connection, you would have a this corresponding Dirac operator, or is it only for some of them?
And as soon as this remainder is strong, you get this. So that's basically how it's made. So we didn't use any real structures, but yeah, the remainder is sort of built in as this perturbation.
But then, I mean, this is, I'm trying to, to understand, because I mean, having assumed that you don't need, anything like or maybe this is the extra condition that you have on this connection, because I mean, classically, basically to any U1 connection, you're going to have a Dirac operator. And I mean, classically, you don't see this requirement. So for instance, would you recover classically that that once you have a principal bundle, then for any connection you can construct the Dirac operator?
Well, I'm not sure if I understand what you mean, because if you lift through this connection, you get an error term, right? So in the Hopf vibration, you get 1/2, and there's this work by Jens and Walter where they always get an error term corresponding to some curvature information.
Oh yeah. No, that's that. I mean, that's correct. Classically, you get something, so you need this remainder term.
Yeah.
But the point is that when you get non-commutative, I mean, it's not automatic that for any connection in the non-commutative sense, when you work with non-commutative algebras, you would get correct Dirac operator.
Right. Okay. No. I mean, you can lift through some connection, but you would need some further sort of extrinsic information to say what you mean by correct Dirac operator, right? So yeah, connections allow you to lift, but they certainly, and they give you at the homotopy level, they're all equivalent operators. But indeed, if you have some external geometric setting that you think is important, then not all connections may be given. I think.
Okay.
Yeah, certainly so.
Okay. Good. Okay.
So the difference of two connections just gives you some perturbation that is that you then need to analyze.
Mm-hmm. Okay.
Branimir, you raise a hand.
Yeah, if I can add to that, I mean,
Yeah.
so we have, there's a sort of change of perspective where, again, the principal connection is this horizontal covariant derivative that lets you glue the vertical and basic geometries together. And as you just very blithely, in general, you will not preserve the total calculus. But the case where you will preserve the total calculus is precisely going to be the case where this sort of relative, this gauge potential, this sort of difference of horizontal derivatives is is a classical vertical differential operator. It really is some sort of like symbol times honest Lie derivatives, like sort of infinitesimal. So it's similar. So if you were to, I mean, I have a preprint that talks just about the differential calculi, forgetting all the analysis, but the intuition you have is that if you take your first order differential calculus and split it into, you have a bimodule strong connection. You split it up into a vertical calculus and a horizontal calculus, and now you can say, okay, I can just vary the horizontal covariant derivative. I think things like this have been considered by Brzezinski, by Djordjevic over many papers, and now you can ask, okay, when am I going to get the same total calculus? And you're only going to get the same total calculus when this sort of relative, this difference of horizontal covariant derivatives factors through the vertical exterior derivative. It's like relative connection one form with post-composing the vertical exterior derivative.
Okay.
In general, so for instance, if you think about something like, so if we work out the example just of like, irrational rotations thought of as a circle bundle over the circle, you can characterize these you can characterize this variation in terms of group cohomology, and the point is that unless your one cocycle encoding this difference of principal connection, this difference of horizontal covariant derivatives is a homomorphism, you're going to get non-isomorphic total calculi.
Okay. You mentioned the word example in what you just said. So now it occurred to me, Bram, could you please tell me if you take for your G-sister algebra just the usual quantum Hopf vibrations. You have SUQ2 sister algebra, you have gauge action of a circle, that's a classical compact Lie group. Acting on a unital sister algebra, definitely it acts freely. I think this is also, this is what we are still trying to prove if it's locally trivial or not, but that's another issue, not relevant directly to your theorem. Would this theorem work? What would these objects explicitly be for this specific G-sister algebra?
For SUQ2?
Yes, sister algebra and the Hopf action of a circle.
Well, you need a spectral triple there, right? And this is not clear what to choose.
What? What do I need?
A spectral triple.
Oh yes. Oh, okay. Yes, you're right.
So this is so we're not constructing a new spectral triple. We're assuming that something was given to us, and then we say, okay, then it decomposes. But with SUQ2, this is the main problem. That also corresponds to what Branimir was saying in a much more general setting, and this problem has been approached by also Jens has worked on this, and Adam Rennie, and so trying to incorporate the SUQ2 setting already as sort of the simplest non-trivial Q deformation setting that you just described. It's not clear what spectral triple to take, because if there are natural objects, there's even a natural connection, but you get a problem there, not with any of this, but the problem when you look at this picture for SUQ2 and you take, say, the standard Potlatch sphere on the base, then this one tensor nabla T, it exists, and even the sum has a nice compact resolvent. But one tensor nabla T does not have bounded commutators with the algebra of SUQ2. And this, in a nutshell, is a big obstruction to what's happening here. And I think this is related to what Branimir was saying, that the horizontal and the differential and the vertical calculi are somehow incompatible.
So it's worse than that, because like it's really terrible, but it's also indicative of what the limitations of spectral triples as we currently know them are. Like in the horizontal direction, you have this failure of, if you like, of metric equicontinuity of the different sort of isotypical subspaces that goes like Q, powers of Q. But then if you want the natural total geometry, which is forced upon you by the Q monopole, and the fact that it's a constant curvature connection, and the curvature 2 form picks up a power of Q squared when you move it back and forth, you're actually going to be forced to take this Q squared one geometry in the vertical direction. So you're going to have a vertical operator that basically whose eigenvalues are like Q squared numbers. And then, as Bram pointed out, you try to take the Q, use the Q monopole to form a horizontal covariant derivative, and your commutators with that horizontal covariant derivative are going to be unbounded in a manner controlled by the modular automorphism coming from powers of Q. So you're unbounded in both directions, and you're actually unbounded in 2 separate ways, vertically and horizontally. So SUQ2 over Podlish is already, like, I'm quite convinced that it's completely outside the bounds of conventional spectral triples.
But if I may add, Piotr.
Sure.
So there could be nice examples of, I mean, of the type you mentioned, not for the SUQ2, but the theta 3 sphere could be thought of as a non-commutative principal bundle over the usual sphere.
Yeah.
Twisting. And then I think, I mean, maybe Ludwig, if he's still around, I mean, I think Zuka, right? I mean, your PhD.
Yeah, Ludwig is around. Yes.
Ludwig? Okay. So I think, there was a little bit in his thesis, and there was something in the paper that he wrote about the construction. And then you can have very nice new examples of spectral triples. So different spectral triples than the canonical one. Then you can construct through strong connection, for instance, a non-commutative 3 torus as a U1 bundle over non-commutative 2 torus. And a completely different spectral triple. So you start with the regular one, and you can get things that are defined by this, so to say, arbitrary algebraic strong connections.
What I can, well, certainly Duka did something in this direction, but what I can add probably is, but okay, that's my invention. Probably you can use modular spectral triples or twisted spectral triples for SUQ2, otherwise it would be quite difficult.
But the problem is you need different modular automorphisms in the vertical and horizontal direction. Because you have Q horizontal and Q squared vertically.
Okay.
Like it's really messed up, but I mean, it's something we have to confront in the long run. I will mention that we can systematically accommodate theta deformation. There's actually this KK equivalence of an undeformed algebra with its theta deformation, and these factorizations are natural with respect to those KK equivalences. And in particular, we can start with something principal and torus equivariant and theta deform it, and you still get something torus equivariant in principle and blah blah blah. But of course, something interesting happens. Like the theta deformed connections, like the theta deformed relative gauge potentials, they will carry over. The theta torus equivariant structures persist. But as you point out, once you theta deformed, you could look at arbitrary horizontal covariant derivatives with the appropriate sort of compatibility, and but if these are no longer torus equivariant, then you could get all sorts of funny geometries on the other side. Actually, no, they'll be so they could still be, if you're thinking about something like SU2 theta over S2, they could still be circle equivariant but not torus equivariant. And so they will be, so there'll be something genuinely non-commutative. And again, this is sort of work in progress with my PhD student, but there will be a cohomological description of basically sort of like the symbol of general sort of relative gauge potentials and again, you get something that you get something like basically you get something weird unless instead of a one cocycle in general, you have a straight up homomorphism. So.
Okay, Tomek, wait, let's finish this train of questioning first. So I understand that there are troubles with Q deformation already at the most elementary level. Fine. Now, well, you could try something perhaps simpler, like the Podlesh equatorial quantum sphere of a quantum RP2, where your Lie group is Z2. Maybe that's simpler. I don't know. But let's leave aside for a moment Q deformations. If I understand you correctly, as long as you simply theta deform your total space in the base space and you leave your structure group, a Lie group untouched, so things work, right?
Yes.
Okay. And of course we have nice examples. We have this nice construction. I think Varili was working on it. S7 theta over S4 theta over SU2. That should all. So you are not limited just to abelian groups and stars and so on.
No, it all applies to those settings. Yes.
Yeah, that's already a good start. But now I'm wondering. So if Q deformations are problematic and theta deformations are more or less automatic, is there some ground in between? Can you give me some pool of examples or even a single example which would not be a theta deformation, which would be genuinely non-commutative and not necessarily Q deformation, maybe something else. Maybe you can have some of these free spaces. For instance, for us, when we studied local triviality, the free quantum spheres, where these are very non-commutative sister algebras. They are much simpler than, say, spheres which have some non-trivial commutations.
I do not know of such examples. It's also, for me personally, the biggest constraint of this result is that you have to start from some spectral triples. So you have to have something interesting, and that seems to be the main obstruction. So you could also try to think about the Kunz-Krieger algebra with its gauge action or something.
Exactly, of course.
Yeah. Or some graph algebra.
Yeah.
The first question is always, what do you take for the global D there, and that is often not clear. I mean.
Yeah, that's definitely true. Yeah, I see that the problem is at the side of equivariant spectral triples. This is what you have to begin with. So when you get started with your theorem, and let's go back again for just a while to this cross product. So if I would take my G-sister algebra to be simply a cross product, so if you want a trivial compact quantum principal bundle, can you then somehow, I know it was already mentioned that not much is known about spectral triples on cross products, but maybe you can comment on this. Can we have some things done when this G-sister algebra is trivial, meaning it's a cross product sister algebra?
With the dual action, you mean?
Yeah.
Well, Branimir, wasn't that also the case that we worked out?
Yeah, no, as I said,
for ZN and
yeah. So there's this generalization by Hawkins, Skalski, White, and Zacharias of a construction of Belisard, Marcoli, Rehani of if metrically equivariant Z the N action, then that spectral triple just sort of you could just plug and chug, like it just falls into place, no problem.
Perfect.
And then what's kind of cute is that the variation of horizontal covariant derivative, the sort of most general possible reasonable variation of horizontal covariant derivative, is now going to be straightforward group cohomology. But unless you sort of like give up on retaining the same total first order calculus, you're not going to see that, because in general, if you have something that isn't a homomorphism, you're not going to get the original total calculus. And actually one thing that's kind of cute is that let me just leave it at that. I mean, I have this recentish preprint that just talks about differential calculi. And then once you're talking about differential calculi, you can just go to town with Hofstar algebras. And so I have an analysis of the sort of the nicest, like the case of straightforward cross products. I mean, it's very, very restrictive in some sense, but you can do this analog of Sweedler Chemology in degree 1 and work it all out. There's this sort of robust sort of group cohomological flavor to the gauge theory in the cleft case.
Okay, thank you very much. I'm happy with this answer. Tomek?
I have a question about Galois cover. If G is finite, then all this vertical stuff disappears. And does the theory simplify in this case?
The vertical stuff. Yeah, well, there might be some natural geometric. Well, but it's more like, yeah, okay, if you have a principal bundle classically with a finite structure group, then there is a natural lift of the downstairs Dirac operator because it's local. So it's a local operator, and you lift through a local diffeomorphism.
Yeah.
And you would see the same in that case. Yeah, you don't, I mean, the module would just be finite. You would have to choose some connection which I guess naturally exists in those cases, which will have a simple algebraic formula, and then you can lift the operator.
Do you need in this do you need in this case a non-trivial Z, this remainder?
Well, the remainder always would wait. Let me think. Okay, let's see where you this is principal. I'm not sure about that.
So I'm afraid to go.
Okay, yes, sir.
Thank you very much.
Bye.
Bye.
I would say that classically, because the connection is also, now it depends on the non-triviality of the cover. Actually, that's that could be an interesting case to analyze. Shouldn't be too hard, but I wouldn't know from the top of my head if you would really get a zero remainder there. I would have to work it out.
Yeah, I mean, finite Lie groups are nice Lie groups.
Yeah. And it might depend on some properties of the cover.
I mean, on that note, there's probably a lot of room to play around with something like a finite quantum group acting on an almost commutative spectral triple.
Yeah.
Think about,
surely, but forget even quantum, Branini. Take it easy. I'm still happy with you being classical. For me, it was truly astonishing to see that we can have beautiful examples of free actions of finite groups on C-star algebras, which are not locally trivial.
Yeah. All right, I also have to go soonish.
Yeah.
Okay, so any other questions? If there are no other questions,
maybe I can have small comment that there are
go ahead.
2 preprints now of my one is which includes the authors, one of my PhD students, Alessandro Rubin with Paolo Antonini, which discusses just this finite coverings. And also another one with myself in which we study some other axioms of Kohn, of reality, orientation, and regularity of spectral triple by discrete abelian groups action on C-star algebras. So a few other actions. That's what I have to say. Okay.
Yeah, this is great, but Ludwig, I hope you realize that when I upload our seminar recordings to YouTube, I have to mark that there are no commercial advertisements.
Oh, sorry.
But anyway, you are not selling the spectral triples. That's a different story. Okay, price tag is 0. Okay, so we are still all right legally. So I think that's enough for today. Let's thank Branimi. I'm confusing your names, guys. You have to forgive me. Let's thank BRAM again for his wonderful talk. This was really exciting. Thank you very much. I really
thanks for having me. And hope to see you all soon.
It's been a pleasure. Let me stop recording, but please don't go away.